When we dream of the other, we inevitably dream of ourselves. For a century, our cinema and our literature have populated the cosmos with creatures that are, fundamentally, actors in rubber suits. 2 arms, 2 legs, I set forward, a head sitting atop a vertical spine. This is not biology, it is narcissism. It is a failure of imagination born from our own evolutionary solitude. We assume that the human form is the inevitable pinnacle of complexity. But the cosmos does not care about our symmetry. It does not care about our spine. Even here, on our own pale blue dot, nature has experimented with forms that defy our intuition. If a slime mold can solve a maze without a brain, and a tardigrade can survive the vacuum of space, why do we insist that a visitor from the stars must look like a slightly distorted version of our neighbor? To understand what lies in the dark between the stars, we must strip away the Hollywood mask. We must stop thinking of life as a shape and start understanding life as what it truly is, a chemical process. A localized rebellion against entropy, dictated by the strict laws of physics and the unique ingredients of its home world. Life, as we know it, is a celebration of carbon. On Earth, we are trapped in the tyranny of carbon, but it is a benevolent tyranny. Carbon is the cosmic champion of connection. It possesses 4 valence electrons, allowing it to bond with up to 4 other atoms simultaneously. Think of carbon as the ultimate Lego brick. It can form long, durable chains, the backbones of proteins and DNA. It is stable enough to hold information for billions of years, yet reactive enough to allow the metabolic dance of life to occur. And the stage for this performance is liquid water. Water is the universal solvent. It dissolves nutrients, transports waste, and provides a stable thermal environment. The marriage of carbon and water is so efficient, so chemically perfect, that many scientists argue it is the only way. But efficient does not mean exclusive. Carbon is abundant, yes, but the universe is vast, and conditions on other worlds are hostile to the delicate chemistry of Earth. In the furnaces of super-Earths or the frozen wastes of rogue planets, carbon chains would snap, and water would be as hard as rock or as fleeting as steam. To find the others, we must look for chemistry that survives where we would perish. Enter silicon, the favorite child of science fiction. It sits directly beneath carbon on the periodic table. It, too, is tetravalent. It has 4 electrons to share. It is the backbone of our digital life. Why not biological life? The Horta from Star Trek, the xenomorph. We love the idea of the living rock. But here, chemistry delivers a harsh reality check. While silicon can form chains, they are fragile compared to carbon. But the true killer is the exhaust.
When carbon bonds with oxygen during respiration, it creates carbon dioxide, a gas. We exhale it effortlessly. It floats away. But when silicon reacts with oxygen, it creates silicon dioxide. We know this substance by another name: sand, quartz.
A silicon-based creature breathing oxygen would literally exhale bricks. It would choke on its own waste products the moment it took a breath. In an Earth-like environment, silicon life is a chemical impossibility, unless we change the environment. In a world of intense heat, perhaps deep within the crush of a super-Earth, silicon chemistry changes. At extreme temperatures, standard solvents vanish, and silicon bonds become more fluid. Here, in a magmatic ocean, we might find crystalline lattice creatures swimming in liquid rock, living on a time scale so slow that to them, our human lives would flicker by like sparks. But we do not need to look to distant stars for strange chemistry. We need only look to our own backyard. Saturn's largest moon, Titan. This is the most compelling laboratory for alien life in our solar system. The surface temperature is minus 179 degrees Celsius. Water here is a rock, as geologically dead as granite. But Titan is wet. It has rain, rivers, and seas. But they are composed of liquid methane and ethane, liquid natural gas. In these hydrocarbon seas, earthly lipids, the fats that make up our cell membranes, would dissolve instantly. Instead, life here might build membranes from acrylonitrile, forming structures scientists call isotosomes. These creatures would not breathe oxygen. They would breathe hydrogen and eat acetylene, exhaling methane. Their metabolism would be incredibly slow, fueled by the faint chemical gradients of a freezing world. They would be creatures of the cold, thriving in a solvent that we use to power our stoves. To them, a glass of warm water would be a vat of boiling acid. Drifting further into the cold, we encounter another potential solvent, ammonia. Like water, ammonia is liquid at specific temperatures, though much colder ones. Ammonia has fascinating properties. It dissolves alkali metals to create electrically conductive blue solutions. An ammonia-based biosphere wouldn't look like our green Earth. It would be a world of blues and violets. However, the chemistry of ammonia is sluggish. Chemical reactions happen slower in the cold. Evolution on such a world might take 10 times longer than on Earth. A conversation with an intelligent ammonia-based entity might require years just to exchange a greeting. They would be the patient watchers of the universe, living in a slow-motion reality. So if we banish the humanoids, what is left? If life is chemistry acting under the laws of physics, we can predict the shapes of the shadows in the dark. On a high-gravity world, a bipedal human would be crushed instantly. Life here would hug the ground. Imagine biological tanks, low slung, with multiple thick legs to distribute weight. Flight would be nearly impossible. The atmosphere would be a crushing blanket. Conversely, in the atmosphere of a gas giant, there is no ground to stand on. Life would be the eternal aviator, vast, gas-filled bladders, living dirigibles, floating on the wind. They would need to be immense to maintain buoyancy, fragile as gossamer, filtering the atmospheric soup for organic molecules. And what of sight? On a world orbiting a dim red dwarf star, visible light is scarce. Eyes would be massive, dominating the face, evolved to capture every stray photon. Or perhaps they wouldn't see light at all. They might perceive the world entirely through thermal imaging, seeing the heat signatures of prey against the cold background of the void. We look for eyes that look like ours. We listen for voices that speak in our frequencies. But the universe is under no obligation to be relatable. The first life we find will likely not be a starship captain landing on the White House lawn. It will be a purple stain on a rock, a strange spectral line in the atmosphere of a distant moon, or a shadow moving beneath the ice of a frozen sea. The reality of alien life will be stranger, more terrifying, and more beautiful than any fiction we have dared to write. We just have to open our eyes and be willing to see something we don't recognize.